Okay. Now to assuage Melissa's anger, I've hit record. So if you're coming back, we're talking about strengths of acids and bases. So if you have a carboxylic acid, they are your middle ground. Now, if you have an electron donating group, it's going to make your acid weaker. So an electron donating group is anything where your first atom has a lone pair like OMe or NH2, or if you had an ester like that, the first atom has to have a that's odd, has to have a lone pair. If it doesn't, it is not going to be electron withdrawing. Okay, so that's the way to tell. Methyls are electron donating as well. They're very weak, but things like NO2, fluorine, anything, if you have an ester, except now the first carbon off is the carbonyl, like whatever this else is, these are electron withdrawing groups. They make acids stronger. All right, so electron withdrawing groups make acids stronger and they make acids weaker. All right, but then it's vice versa for bases. For bases, they are going to make bases weaker, but electron donating groups will make bases stronger. Does that make sense? Yes. Okay. So let's go ahead and go back. So we don't incur the wrath of Melissa. She is small but fierce. Actually, if I'm afraid of anyone, I'm afraid of Maggie. She's top three I'm afraid of. Forcing me to go buy her boba. I'm just kidding. Okay. So now for question 9, it says, which of these labeled protons is the most acidic? I mentioned this before the break. Do you guys remember what I said when it comes to hybridization? What's the difference between all the carbons that they're attached to?
Would it be how many like other things it's attached to?
It's the hybridization.
Yeah, hybridization.
Yes, that's the fancy chemical term. So this is something you need to remember. sp carbon hydrogens are going to be more acidic than sp2 carbon hydrogens, and they're going to be more acidic than sp3. As a rule of thumb, the pKa is about 25, this is about 44, and then this is about 50. So those are logarithmic scale differences. So that's 10 to the 25th times more acidic. So terminal alkynes are extremely acidic, and you can deprotonate them relatively easily. And the sp thing, yes. Hybridization, Matthew. Hybridization. Okay. Question 10. Which of the labeled protons is the most acidic? Which of the labeled protons is the most acidic? Oh God, no. That would be very tough to rip off. Remember, it was kind of like that idea of the problem you did where you wanted to substitute the bromine, right? And like we talked about how easy it was. An sp2 like substitution is very hard to do. Nope. The key is, the way to think about it is that if you were to remove your proton, right, you would have a lone pair on A, right? Or you would have a lone pair on this carbon, a lone pair on this carbon, or a lone pair on this carbon. And so the question here is, what do you think is going to be the key indicator in terms of it's going to be easy? I'm going to tell you right now, removing a benzene proton is really hard to do. So if you ever see an option to say which is the most acidic, that should never be your first choice. If it's the least acidic, then you should say that. To me, that looks like a good one. Your benzene protons are probably going to be your least acidic, but most acidic. So now looking at the rest of these, which one do you think is going to be your dealie? Any idea? Yep, C. And why do you think C, Matthew? There's a magical word here. Nope. That would only really count if it was. I mean, that does help, but that's not the specific reason. If I draw this, what's the magical thing you guys can draw? It's an R word. No, arrow pushing is how you do it. Resonance, resonance. This has two resonance forms where I can go to the left like this. That gives me my second one, or I can go to the right like that. So remember, when you take your proton away, a good way to think about how strong that acid is going to be is how stable it is once you remove it. So if you do this, you get three resonance forms. The more resonance you get, the more stable it's going to be. So in this case, taking a hydrogen between two carbonyls like that, very acidic. Make sense? Okay. Question 11. What is the stereochemical relationship between the following molecules?
Okay. Aren't they identical or am I just dumb?
I don't feel that there is a polite way to answer that question.
Okay, I see what you mean now.
You're not dumb.
Well, they look the same to me. There's like a plane of symmetry like right there, basically, in my head.
Okay, so Gwen, Maggie, Matthew also says A. Do you agree?
I don't know. I don't think they're identical. I'm not entirely sure though.
Okay, Maggie says C. And the correct answer is going to be C. Any reason why? Yeah, so remember, they are mirror images of each other, right? So remember, if you were to put a line here and imagine that this is my, if you imagine that I had a mirror here, they're reflected, right? They're just mirror images. If you wanted to double check just to be sure, because I know you guys love to be sure on stuff. This is what my two rings look like when I draw them out as flat planar molecules. So now what was the one thing I told you you guys could do when we were on this? I know this is a couple units back, but what was the one thing I told you you guys could do to double check that if you're unsure about something being an enantiomer or identical or whatever?
Count the carbons.
No. Well, I mean, obviously you should have the same number of carbons. That's counting carbons really only comes in handy when you are doing your mechanisms. But this is nope. Flipping is when you're doing like your which one is more stable. This is something related to stereochemistry. What were the magical letters you guys learned when you did stereochemistry? S and R, remember? Remember, an enantiomer is when you flip all of your stereocenters. So if you have a stereocenter that's S, the enantiomer will be R. So if you had a stereocenters, like 3 of them, and they were S, 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 then the enantiomer would be R, R, R. So what you can do is that you can attempt to figure out what the stereocenters are. So for on the left, this one is R, and then this one is, this one is also R. On the right, this is S, and then this is also S. So are my stereocenters different now? Are they opposite? Yep. So you can check your stereocenters and see if they are opposite. If they are all opposite, then they are enantiomers. But the fact that they are mirror images should be a good indicator. Questions? Have you guys just kind of pushed all of your extra information out of your head once you learned it? Which is completely fair. Okay, which statement about the following projections is correct? Okay, we got D. Okay, so again, what is the easy way to figure this out, this type of problem? I say easy, but you figure out what the stereocenters are. So this is R, S. This is going to be R, because this is R. This is going to be S, and then this is going to be R. And then this is going to be S, and then this is going to be S. Okay, so 1 and 3 are enantiomers. It is true, right, that they flip, but what else? What is more important about them? They are opposite stereocenters, so one's R and one's S with the plane of symmetry. So what is that compound technically? They're meso. So 1 and 3 are actually going to be identical, because if you are both meso, right, and you have the same you have the same structure, then they're identical. So 1 and 3 are actually identical. They're not enantiomers. That's the way that they try to trick you there. 2 and 4 are identical. RR and SS. Nope, that is incorrect because they are opposite stereocenters. 2 is a meso compound. Nope, there is no plane of symmetry. And D, 1 and 2 are diastereomers. Yes, and 1 and 2 is going to be correct. All right. So I would recommend that you guys go back through and review your stereochemistry stuff. I'll see if I can dig up a note packet for you guys and some practice problems again so that you guys can do that. I'll send it to Maggie and Gwen and Matt, whoever else emails I have right off the top of my bat, and then we will go from there. All right. Questions on that one? Okay. Next up. Which of the following are meso compounds? Which of the following are meso compounds? Matthew has B. Okay, Matthew says D. Gwen says B. Gwen, I'm coming to you now. Don't let me down. Why can't number 1 be a meso compound?
Because there's no stereocenters.
Correct.
Okay. Oh God. Thank goodness I got that right.
It's all right. Let's review. And this is the important thing, right? Is that typically when we think about our meso compounds, typically our meso compounds have 2 stereocenters, and then we have a plane of symmetry between them. All right. So in this case, our meso compound is not going to have it's going to have that plane of, it's not going to have that plane of symmetry. So in this one though, since 1 doesn't have any stereocenters, it can't be meso. So 2 is my only option. All right. Question 14. What would the stereochemistry of the following reactions product? So we do an alkene addition, hydrohalogen addition reaction. So which one do you guys have for this one? Yes, remember, what do you form in the first step, right? What do you form when this double bond grabs the proton? What's your intermediate going to form? Carbocation. Remember, anytime you form a carbocation, right, you are no longer going to have any stereospecificity, meaning you can get both the R and S. So you should get a racemic mixture. So anytime you have a carbocation in your mechanism, you are most likely going, and you get a stereocenter, you are most likely going to get a racemic mixture. All right. This is also true for our radical chemistry as well. Okay. Yay. Yeah, I know you guys love these. What is the order from most to least stable of the following conformations? What is the most stable? Maggie, I will visit your grave and I will leave a fresh boba and a flower. Does that sound fair? Okay. Later, I'll see you Saturday. Okay, so we got A from most to least stable. Okay, so Gwen says D, maybe. So when we have these Newman projections, right? What do we want the relationship to be for our biggest groups? We want them to be what? We have gauche or gauche, however you say it. We have anti, we have eclipse. Do you remember? Anti-conformation. All right. So on your front carbon, right? What is on your front carbon? What is your biggest substituent? Chlorine, hydrogen, or CH3? Nope, CH3. So the reason why CH3, don't forget, and this is a common error, is that chlorine is a big atom, right? But don't forget, carbon, even though it's smaller, still has hydrogens coming off, right? So its actual volume is going to be larger. So anytime you have like a methyl, an ethyl, or anything like that, those are going to be larger than your halogens, mainly because you have those additional hydrogens coming off. So it takes up additional space. So in your front one, your methyl is going to be the largest one. And on your back carbon, what is your largest group? The alcohol. So if we look at these, in 2, my largest groups are anti to each other. So 2 should be my most stable, right? In 1 and 3, they are gauche to each other, they're gauche to each other, but in 1, it's between both the chlorine and the methyl. In 3, it's next to the CH3, but it's opposite the chlorine. So it's going to be 2, 3, and then 1. Does that make sense? Okay. Question 16. Which of the following products would yield a miso product? Which of the following product would yield a miso product? Okay. Matthew says B, he's confident in that one. Gwen is still riding that fence between B and D. So the trick for this one is you've got to ask yourself, what are you asking, right? Or what are you adding in each one? In A, you're going to add a hydrogen and an alcohol. So that won't give you a meso compound whatsoever, right? You will make a stereocenter, but you're not going to have, you won't have a plane of symmetry. So that's not going to be an issue. In this one, you're going to add a, oh, sorry about that. In this one, you're going to add a hydrogen and a chlorine. So then again, this isn't really an issue. In B, you're going to add 2 bromines, but 1 bromine will be a wedge, remember? And then 1 bromine is going to be a dash. When you do D2, which is deuterium, which is an isotope of hydrogen, remember this is the, you are going to add the deuteriums in a syn addition. So now it should be this one. So your answer should be D. All right. "17. Which of the following molecules could have an enantiomer? Which of the following molecules could have an enantiomer?" I know you guys are going to get this right immediately. Yes, Gwen is correct. Gwen, walk us through this one. Or if you guess, that's fine too.
I kind of just guessed based off the previous problem that we had.
That's completely fair. So what's interesting about A? What does A have between its 2 stereocenters?
Plane of symmetry.
So then it's going to, what is this one then? It's meso, right? So
Yeah.
meso compounds, if you, the enantiomer is technically the same thing. What's unique about C and D? What's wrong with C and D? It's written in a way to trick you. Does C and D technically have stereocenters?
No.
No, because if I look at this carbon here, it's got the OH, right? And then there's a hydrogen that's not drawn. But if you go 1, 2, 3, you get to a carbon with OH. 1, 2, 3, you get to the same carbon with the OH. So those are the same things. So both C and D have no stereocenters. So can't have an enantiomer if you don't have a stereocenter. Therefore, B is my only option. Okay. Next one. The product of this reaction will be achiro, but not meso, a mixture of diastereomers, a meso compound, racemic. Well, we're just blasting through this. Gwen is correct. Gwen, do you want to walk us through this again? So which carbon is going to get the hydrogen and which carbon is going to get the chlorine?
Geez. Is the chlorine gonna go to the carbon that's underneath the methyl group?
Yeah, so this is what your product is going to be, right? Is you are going to add it to this one. So you're going to get this product where you have your methyl, like here, and then your Cl here. So did you create a stereocenter, Gwen, when you did this?
No.
Nope, because you go to the right, CH2, 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 you go to the left, CH2, CH2, the same CH2. So since both sides come to the same carbon, it's not a stereocenter. It's achiro, but it's not meso. So since there's no stereocenter, it can't be a mixture of diastereomers, you can't be a meso compound, you can't be racemic. Does that make sense? Looks like a flower. Keep walking, hippie. I'm just kidding. Okay. What is the most stable conformation for cis-1-bromo-3 methyl cyclohexane? Which one is the most stable conformation for 1-bromo-3 methyl cyclohexane? A, B, C, or D? I was just going to ask you guys, Mag, can you eliminate any answer right off the bat? If you haven't died. You can eliminate C right off the bat, right? Why can you eliminate C? Because your CH3 and your bromine are pointing opposite directions, and that's the same for D as well. Bromine's up, methyl's down on the right one, or bromine's down, methyl's up, right? If they're cis, they have to be pointing the same direction. Okay, so now your choices are pointing up axial and pointing down equatorial, and as Gwen said, because it's equatorial, B should be the correct one. Does that make sense? Okay, so this is a good place to stop. Any last minute questions for the evening, because I've got to make a PowerPoint and grade homework and other stuff. So and eat my dinner. So do you guys have any questions right now about these problems we've done so far? Okay, so the important thing is what do you think is going to be the most useful thing to help you guys in terms of studying? You can do these problems and you can do the Jeopardy stuff, but what else do you think is going to help you?
A cheat sheet?
Making a cheat sheet, but then going back through your previous exams is going to be helpful. Go back and see where you struggled, right? Because if you've learned something before, you may have forgotten it, but it's probably still in there. So go back and see what you can pull out. But also start making a cheat sheet for your functional groups, right? Make a cheat sheet for your reactions. Mags, I know you have cards and stuff like that. So if you had them for previous tests, just get them out and start looking over them again. We can meet Saturday, and if need be, we can meet Sunday before your exam, just in case you guys are feeling a little bit stressed or whatnot, and we can keep working through this. So I will see you all, well, those who can make it Saturday at 4 p.m. your time. I hope you guys have a good rest of your evening.